Swayam Prabha. Digital India. Educated India.
So, the last class where we started was we started looking at the volume averaged multi-fluid models, and we started to, if you recall the equation, we first did continuity. Let me change the marker to blue. We did continuity, and this was using the volume averaging technique that I showed. This was the expression that we wrote. Okay. Now, this particular stuff actually designates the mass transfer from all other phases to kth phase due to phase change. Okay. Now, this we said is equal to summation of j equal to 1 to all the phases phi, but j is not equal to k. Okay. So, this is m triple prime j k. Okay. So, from all other phases it is actually summed over j. So, therefore, from all other phases how it is transferred to the kth phase. Okay. So, this basically represents the mass per unit volume. Okay. And we also said that m triple prime j k is the same as minus m triple prime k j. Okay. So, applying now, converting this and also recalling that rho k is nothing but epsilon k rho k. This is the intrinsic and the extrinsic phase average. This is given as epsilon k rho k k plus epsilon k rho k k into v k k plus that is the expression that you get. Okay. These are basically the dispersive term which we defined in the last class, right. So, that is the dispersive term. We saw that what the dispersive terms are, right, in the last class. So, if we neglect this dispersive term, in many of the cases they are actually small, right. So, neglecting dispersion, what we get is okay. So, that is what you get. Okay. If you neglect the dispersive term, this is the net equation that you get. This is the continuity equation. Okay. So, now moving on, Let us go to the momentum equation. Okay. Now, the extrinsic phase averaged momentum equation plus okay. So, this is basically the body force term, same for different species, if we assume it that way. Okay. Now, as per the rules that I covered in the last class, if you recall the rules, okay. So, the first term will be, okay, you can represent this as minus 1 over delta V A k d A k. Okay. Similarly, this particular term, the second term, the second convective derivative, the second part of the convective derivative is given as okay. Okay. Similarly, the third term which is basically the stress term that we have, okay. And the last term okay. So, what we do is now we combine all these three terms, all the terms, not 3, 4 terms together. Let us move to the next. To the combining. Okay. Right. So, that is the total equation, combining all the things together, the momentum equation, right. Now, we can also from an intrinsic point of view these are the expressions is equal to, these are long lengthy equations, but it is required to understand the physics of the problem. Rho k v k minus v I dot n k d a k plus, because of these additional terms that we are carrying, because of the transformation that we did, okay. So that is the expression. That you get. Whereas here tau k prime k is the phase averaged, stress tensor. It is a phase average stress tensor, okay, for the kth phase. So that is what you have, right. So that is what it is. So this stress tensor can be further written as corresponding the pressure, this is the viscosity, minus 2/3 mu k okay. So that is the stress tensor that you see. Now also if you go back to the previous one, let us put a couple of thoughts on these, on a few terms, okay. So for example, this particular term over here, change the marker, this particular term that you have over here, what does this designate? This designates some kind of a momentum exchange, right, okay. Now the term, this particular term, what does this designate? This designates some kind of an interactive forces, between all other phases and the kth phase, got it, okay. So that is interesting. So you can see that this is the nature of these two important terms, that the additional terms that we have carried. One is that one represents the momentum exchange, the other represents the interactive forces, okay. So if we go to this next page where we actually did all these things. So the momentum exchange term, if we look at it, okay, when we tell that it is momentum exchange, then it can be cast in this particular form. Right. So that is the mass that was exchanged, okay, and this is the corresponding velocity, okay, at the interface, okay. So the intrinsic, this is intrinsic phase averaged velocity, of kth phase at the interface. So, it is the intrinsic phase averaged velocity of the kth phase at the interface. Okay. Similarly, so we know that what this term will be. This term on the other hand, the interactive force term, okay, can be represented by some kind of a force expression now, J not equal to K, given by some kind of a Fjk. What is Fjk? This is interactive force between the jth and kth phase. Okay. So, f jk is equal to minus f kj and can be written as some kind of a parameter kjk, which we will come later what that parameter means. This is called something called a momentum exchange coefficient. Okay. So, momentum exchange coefficient. So, this essentially means that this is an ad hoc kind of a term, and these are the velocities in the intrinsic phase average velocity in the two phases. So, this is a momentum averaged quantity. So, determining this particular quantity between phase between phases j and k, okay, is difficult, right. It depends on the structure of the interface also, right. So, it is highly dependent on interface structure. That is a very crucial thing, right. So, how do you actually determine it? So, if we for example have a vapor and a liquid system, like can be vapor bubbles or liquid droplets, whatever it is, the kjk is given by 3/4 CD Ej rho k dj Vjj Vk k. Okay. So, this is basically the diameter of bubbles or droplets if it is a system like that. So, this is a very ad hoc example. This is the drag coefficient. Okay. So, that is the drag coefficient, this is the total expression. So, this is like one for liquid vapor system, this can be cast in this particular fashion. Okay. So, that is one way of casting the whole thing. Okay. So, now if we assemble the full momentum equation, and this is just one example that we gave, as the whole momentum equation becomes this is the full momentum equation. Okay. So, the full momentum equation attains that particular form. Okay. So, that is one thing. So, let us move to the next page. We can also similarly do the energy equation. So, once again we start from the extrinsic phase averaged. So, That is the extrinsic phase averaged equation. Okay. Now, if we look at the each individual terms of this particular expression, once again this term will be rho k h k dt minus, these are long expressions as I said, and sorry. So, h k v I dot n k d a k, that is the first one. Okay. Similarly, the second one you can write it in a very similar fashion. So, similarly this third expression, okay, and so similarly this particular expression over here, or the pk expression, can be written as, so these are all just you apply the rule, that is it. Okay. So, I am not putting the ak always, because you know that it is taken with respect to the ak. Okay. Similarly, the contraction part, this particular part of the expression, tau k is almost equal, this is equal to that, and this is equal to v k tau k plus 1 over v ak pk nak dak contracted on the tau k. Okay. So, that is the expression that you get. So, each and every individual term is in this way taken care of, and if we neglect the dispersions, which we have done in the case of your continuity and as well as in your momentum expression. Okay. And so, that is an important part, because if we neglect the dispersion part, then all those additional quantities will just go off. Okay. So, if that is the case, then we can write it in a holistic fashion. this is Nk plus okay. So, this particular part what you see over here, okay, this Pk, sorry, this is actually Pk. So, this is basically the work done by the pressure and shear stress. Done by pressure and shear stress at interface. Okay. So, this basically completes this part of the energy equation. So, you know the individual terms. If you look at it, it is pretty obvious that this and this terms are particularly important, and we will see what those terms are in the next lecture. But right now, so what we have done is that by neglecting the dispersion of part of the energy equation, we have been able to cast it in terms of these equations over here, right. So, we will see that what happens when you actually take the full volume averaged equation in the next lecture. So, we will stop here at this particular point and we will take it up in the next lecture. Okay? Thank you.